Hello, everyone. Give us a couple minutes to wait for a few more participants to sign on, and we'll be starting in a couple minutes. All right, I think we can get started as people continue to sign into the webinar. Um, so first, I want to welcome everyone to Omnex's webinar on the prevention of manufacturing and assembly defects using principles from design for manufacturing and assembly. Our presenter today will be Michael Papanis. He is our Director of Strategic and Continuous Improvement Strategies. With over 38 years of experience in automotive manufacturing, he's held leadership roles in the areas of advanced engineering and new model launch. He has developed and implemented standardized manufacturing plant operating systems in safety, quality, delivery, maintenance, and costs. He's also led team-based organizations on the plant floor, driving continuous improvement and employee engagement. Using statistical problem-solving methods like 8D, design of experiments, 5Y, and a 7-step process improvement methodology, Mike has led numerous projects in engineering offices and transactional processes, including engine control strategy. He has also led multi-party academic and industry consortiums in R&D for advanced manufacturing methods and technology. So without further ado, I'll hand it over to Mike and let him start the webinar.
Great. Thanks, Andrew. And welcome, everyone. Yeah, glad you all could make it today. We're going to have kind of a fast pace. Now we're going to get through some of these topics today. Pretty interesting stuff. It's all about how do we actually run the shop floor more easily based on product design and ultimately some process control. So let's get on. Let me get ourselves started up here and get going, eh? There we are. A couple quick cleanups here. All right. Great. So yes, again, welcome. Glad you all could make it. And looking forward to y'all learning and seeing a few things, maybe supporting some things you already know and learning a few things that might help you going forward. So preventing manufacturing and assembly defects and really looking at one of the fundamental, if you will, design for manufacturing and assembly methods and error proofing. Now that's what we're really going to be going through today. And we're going to be talking about some of the common defects, what are out there, what are the benefits from what we're talking about today? How do they help us? How does it really manifest itself in the production systems? What are some rules and things that we can use when we're looking at simplifying our designs? We're going to be talking about simplifying some methods around simplifying designs, both in the product side and downstream in the manufacturing processing, right? So design for manufacturing, design for assembly, some rules and some error proofing techniques that go along with it that get us into prevention. And when we have to, of course, inspection and correction. How do we avoid some of the correction piece, especially? And then how do we actually integrate some of these rules, these design for manufacturing and assembly rules into our product development system? And some of the things that are going to be fundamental to making us successful in the way we do work when it comes to actually simplifying our overall production system, really focus on getting cost out as a result. That's really what we're going to be looking for by simplifying our designs and simplifying our processes as a result. And then how do we sustain this? We're going to talk about some metrics that we can use. I know everyone's got scorecards and plenty of metrics and measures that you're already keeping track of, but to just lock in some of the things we're going to be talking about today, to be more disciplined in the way we do our work, how do we measure the effectiveness and the use of these concepts we're going to be talking about? Design for manufacturing, design for assembly, and some of the error proofing tools that can go along with it. So let's get into it. Yeah, anyone ever get a product or a process that looks like this? How great, no, how robust a process is this? In case you can't tell by first look, although it does show down here at the bottom left, in case you don't recognize this is your pencil sharpener. Yeah, have you ever felt like you were in a system that looked like this? Have you ever asked the question, can we make it any more complex? Yeah, just to kind of set the stage, this is how it feels sometimes being in manufacturing, trying to make some product that you got to go through something like this. Again, oops, this is a pencil sharpener. If there's any question on how this works, a pencil sharpener, of course, every pencil sharpener has to have a window, right? Through which you would fly a kite that's attached to a string through a pulley that when the wind blows, there's a cloud right here. When the wind blows, opens a gate for a group of moths to escape from their cage. And of course, then they can attack a woolen garment that's hanging across another pulley system, counterweighted with an old shoe, that when the weight goes towards the shoe throws an electrical switch connected to an iron that's on a pair of trousers, stationary. I say trousers because there's suspenders on here. Long enough for that to smoke the trousers that hopefully goes into a little tube in the hole in the tree, wherein there is a rabbit living that aggravates the rabbit enough to jump into a basket, once again cantilevering across a branch, opening a cage for a woodpecker to finally have access to our pencil that's held on some kind of fixture. Yeah, this is what we're trying to avoid, of course, in the extreme. And of course, here's our corrective action down here. Just in case something in here goes wrong, of course, we've got a pocket knife, so we can actually still get the pencil sharpened. This is what we're going to be avoiding, right? Just to kind of baseline us on how this thing goes forward. So what we're talking about, first things is this idea of design for manufacturability. Can we make the part? Can we make it? I like to talk when I put this class on and I actually go into engagements to work on products. So, part of what we do at Omnex, of course, is training, but in hands-on work, especially when it comes to this type of engineering work, design for manufacturing and assembly. The first question I always tell these folks are you making products that your manufacturing system can make? Because if you're designing products that you can't make, you don't have a design. So we're really talking about design for manufacturability, optimizing the entire system. Are there going to be trade-offs? Absolutely. Do you need to deliver on the requirements? Positively. But if you can't make them, you don't have a product. So we're going to be talking about the full actual life cycle of the product: concept, development, design, manufacturing process engineering, in the field performance of the product, as well as serviceability of the product, looking at cost, reliability, and considering any type of statutory regulatory issues. Design is not easy. I don't mean to give that impression, but if we can't make it through our system, then we don't have it. And our system includes fabricating, procurement, suppliers, service, and repair. And so one of the things that we really focus in on, one of the key, as it reads, pillar of being successful in making and designing products that our manufacturing system can actually produce is not an uncommon term, but a hard one to pull off all the time: concurrent engineering. And that's where APQP, Advanced Product Quality Planning, comes into, as shown here at the bottom. Phase gate approach, sure, that's certainly one of the most popular ways. There are other set-based design methods, but there are always checkpoints along the way that are engaging cross-functional teams between the checkpoints with deliverables at the checkpoints. Concurrent engineering, where we have these different groups of product development, prototype, manufacturing engineering, production, purchasing, and maintenance people engaged cross-functionally, concurrently in the development and design of our products. So what are some of the opportunities? What are some of the drivers that we really take into account when we're talking about these things? Well, of course, time is money. So whenever there's time in the production system, there's money there. Labor and overhead burden, as being the, cycle time being a measure of some of that as well. Assembly time. How about assembly levels? How many different subsystems are in my design? Methods, the actual methods, how complex, right? Any redundancy. Packaging, huge item from what cost drivers, from protecting the product and from obsolescence of the product and damage. What's the right volume that we're making to? We want to make sure we're always matched up. These are cost drivers. Options, right? How many options are on our final product going out the door? How many combinations of subsystems and features and offerings are there? How do those multiply up to the complexity again of the product? And then, of course, variation, which is everywhere: man, machine, materials, methods, measurement systems, right? Environment, and work imbalances, station to station imbalances, tolerancing. Anyone that's in manufacturing, of course, can appreciate the impact of tolerances that don't meet the capabilities of our existing system. And the extra handling, waste, as we know, is, you know, the 7 wastes that we covered last week or 2 weeks ago in our Lean Six Sigma discussion. Of course, part availability, line outages for whatever reason, downtime, part supply, and then the rework, huge cost driver. How about on the make side? I don't want to get us too lost in assembly versus manufacturing. Manufacturing is you're making it, you're creating a part. I used to be in casting, and casting we used to joke around saying, hey, here we make stuff. Everyone else either pokes holes in our stuff that we make, or they attach it to something else. Manufacturing, right? Materials, processing, complexity of toolings, non-value added tolerances, handling issues, size, standards that vary from supply or from customer to customer, or site to site, or country to country, wherever you might be operating. How about how many prototypes? And this also holds in the final assembly of the product as well. How many prototype and prototype levels do we have to have to prove design intent, right? And of course, variability is there as well. Variation is everywhere. So what are some of the immediate kind of solutions and techniques that we're going to be talking about today? Common components. Yes, that helps with a lot of the complexity and system costs and familiarity with the part in the performance in the field, warranty, common parts, easy error proofing, easy alignment. We're going to talk about some rules that will support each of these techniques that we're just showing here. Handling. How many times do I have to pick up the part and move it? How many times do I have to reorient it? Minimizing the number of tools. How many secondary and tertiary levels of tools, fixtures, jigs, tool bits do I need to put this stuff together? How about symmetry? I'm going to go asymmetrical or symmetrical. Symmetry of mating parts. We'll have some rules around those. Communication. Absolutely. Remember we talked about concurrence? Yeah, well, concurrence and continual communication. Any kind of automation. No blind operations. These are not the rules. These are some of the techniques, let's say strategies to get there. Self-attaching, use of gravity. How about if we had designs where we didn't need final adjustments? And how about if we build on rigid bases or fixtures? So those types of strategies, if you will, really start to lend a direction and what are some of the rules behind those strategies. One of the key things we're going to be talking about is getting the number of parts down, the actual part count down. Right? That's an important element in the overall total cost. Not only in the cost of the development, design, and test. But of course, the ongoing bigger costs, ongoing costs in the production world with additional processing and machinery and equipment. What's the cost of just getting a part in our management system, in our part bin, if you will? This is just a quick look, a very simple part. And it's actually total cost just to have it in our part bin. From the engineering, test, manufacturing, purchase, inventory, and logistics, $27,000 just to put a very simple part into our system, right? Just to add a part, right? I know in very large automotive OEMs, it can cost up to $1 million just to get a part into the system, right? Not even using it, just having that available for us to pick from. So when we look at the opportunity costs, when we talk about reducing the number of parts and the use of some of these rules and evaluation techniques that we're going to talk about today, here's what's available to us. And this is from years of study that actually came out of automation world on operational savings from using design for manufacturing and assembly techniques regularly and in a disciplined way. Throughput, 68% opportunity by making components easy to assemble. Factory floor space, how many square feet can we get back in our factories because we're not putting extra machinery and processing out there for complex parts? Floor space, just floor space. And that floor space really provides um, opportunities for additional product to come in. One of the things that we found at Omex as we've worked over the years in this field of design for manufacturing and assembly is by reducing the number of parts, you reduce the number of machines in the existing floor space that we can put other machines in for other product lines and have even more profit opportunity. How about supply chain management? 42% reduction opportunity there. Inventory, just carrying costs of the parts, about 37% reduction opportunity. And change orders, yes. Think about if you're in product development, where are you spending your time? Engineering change orders, are you designing new cool stuff? Reducing the amount of workload upfront by applying some of these rules and evaluation techniques for simplifying our designs reduces the number of change that needs to occur, especially through launch, that bogs down our product development system in fixing things instead of developing new things. 37% right here. And then just in the documentation itself, documentation. So all these documentation, another 37%. All of these individual factors can be reduced by significant amounts. So what are some of the success factors we mentioned already? Concurrent engineering. There's no such thing as starting this early and having a process and a procedure, a process that everyone follows. Let me just mention again, in my experience with design for manufacturing and assembly, almost everywhere we've gone, everyone says, oh, hey, Mike, we already do this. I mean, when I'm designing, I work with a lot of designers and engineers and absolutely bright people. And now all the time we're saying, yeah, I know. Hey, I always think about this when I do this. But we're working in a product development system. Do we have a common approach, a standard approach that we continually evolve as we learn so that we use this regularly, predictably, and improve upon it? That's one of the key tougher points that we'll talk about later in the discussion this morning around implementing the use of design for manufacturing and assembly across your product development system, right? So we really are talking about a process here that involves the people, continually improves, and still takes into account trade-offs. We all know design is about trade-offs, absolutely. That's where trade-off curves and limit diagrams are cause and effect diagrams as well come in hugely important. We're not throwing any of that stuff out. What we're doing is looking to see how can we simplify our designs so the overall workload is reduced. So we're delivering more value to our customers. Now, customers if they ever knew whatever some of the stuff we do in product design, they'd say, "Oh, wow, really? I'm paying for that?" Value always defined by the customer based on what their requirements slash performances over what they're paying for it, right? And when we're talking about engineering change notices and additional work because of the complexity of our designs, that's not value, right? We're talking about getting that kind of waste out in the product development system and not allowing it to manifest itself in the manufacturing system. So design for assembly, yeah, it's a tool, it's a method for design teams working with their counterparts in manufacturing, manufacturing engineering, production, maintenance to optimize a part design to drive cost to their minimum and drive the number of parts to an optimum number of parts for ease of assembly, for ease of assembly. So classic example here on the left, started with 2 parts, not very reliable on the assembly. Lots of waste, there's no rework in this. Lots of waste, a lot of very long cycle times to get this right. Well, you know what? This is a classic example. We actually added 1 part, but the overall assembly cost came down from cycle time, rework, floor space even on this particular one. So we're really looking at how do we optimize and really make our assembly system and our manufacturing system work for us. On the manufacturing side, design for manufacturing, it does look at the complexity of the individual part, and its difficulty to manufacture, trying to drive it to make it easy to manufacture. Here's just a classic example of a plate with a lot of milling, drilling, and bushings, and look at all these different holes. The question is always why, right? Why these holes? Why different dimensions on some of these holes? And the answer is always, in the near term, always come back, well, Mike, it needs to mate up with something that's the same diameter. Well, why does that diameter have to be whatever that diameter is? We're talking about using these tools initially way up front in the system, from the concept to the system stages, from the system to the early design, second, third level design releases, finally, where we have a lot of design space, right? And so we push back all the time, especially on the part level, for the manufacturing side to optimize it as well. Think of the different drill bit sizes and milling and drilling and paths, and this might be why, what's going on here. This up early in the design stage, when we talk about concept, is when we really start to apply some of these specific rules that we're talking about. We say in the concept, we're going to see some design rules and principles that we're going to talk about those up front, and they're around simplifying things. Then into the actual design rules around design for assembly, looking at part count and the assemblability of those parts. And then applying some specific rules around automation and manual considerations for the assembly. And then for the design for manufacturing, looking at the actual component level to optimize that side of the system when we then get into the final detailed design. The detailed design should, in this approach, which is a little bit higher level here, is it's taking our simplified designs and just honing them in. So some advantages, as I've been saying, fewer parts, less stuff to make, less opportunity to reject and have, as a result, higher quality, less material, less energy, faster through the manufacturing system, dock to dock, which is always time, right? Time is money. Taking the viewpoint of the part, going through your manufacturing system. Simpler parts move through the system faster, right? So they get to market and cash flow is improved, right? Faster assembly, easy to assemble, all leads to lower costs, more profit. I found this guy kind of researching when I was looking around for how do I kind of help get some thinking into our head when we're going into an actual design effort when we're doing this in an implementation. And I found this guy, Antoine de Saint-Exupéry. I was told how to pronounce that in one of my classes, but perfection, he said, perfection is reached not when there is no more to add, but when there's no more to take away. Yeah, I think that's a good way to kind of set our tone here when we're getting into the next steps around some of the rules and the evaluation methods. Also, as I found out, this is also the guy who wrote the book Le Petit Prince, the Little Prince, back in the 30s. So, yeah, nothing left to take away. Because here's, again, one of the things, this is from actual case studies that Amex has gone through over the years. These are the more recent ones in the past 5-6 years. Working with a medical device manufacturer, they got their part reduction. They 19%. They took almost 20% parts out working through this with us. A stereolith machine manufacturer, service. One of the key things around design for manufacturing and assembly we'll see is also serviceability of your components in the field. 45% time reduction they experienced by simplifying their designs for in the field service. Automotive engine manufacturer, throughput 12% up. Jet engine manufacturer, assembly throughput up 9%. And then also a personal safety device producer, their quality increased 12% by using these methods that we're going to be talking about. Design for manufacturing and assembly, and the drivers for those that we're talking about next here, design FMEAs and process FMEAs. There certainly is a connection. Design FMEAs is when the engineering team, product development team is looking at the failure modes to either design in controls in their products to address those failure modes or eliminate them. Now, the RPNs or AP values that come out of that exercise, that is an engineering exercise. And that is where we find the opportunity to really apply design for manufacturing and assembly rules to specific designs, specific failure modes. So when we look at, if you will, the APQP phases and the specific deliverables that occur along the way here, we're really talking about looking here. There's our opportunity. We talk about developing process flow diagrams based on designs, process FMEAs, control plans, work instructions. That's where all the control really starts to manifest itself. Up early is where we start to really look and say, hey, this is where we start to apply design for manufacturing and assembly to drive those RPN numbers down through design. Hugely important, because when we get to the stages of process FMEA, right now we're focused on how do we hone in our manufacturing system to then lock in those requirements so we have a production system now that produces with fewer errors, driving off of those simplified designs. So we look at feasibility, manufacturing feasibility, manufacturing process feasibility, layouts, bill of materials. This is the kind of stuff we look at that eventually drive to work instructions. Last chance for gas, I like to say, for quality. If we're simplifying our designs, we're going to be driving it through, let me go back for a second. We're going to be driving it through this process. Simplifying designs, simplifying and locking in controls in our manufacturing process so that the whole system gets easy. Manufacturing should be easy. I don't want to sound naive here, but think of that also as a goal. So when we talk about this stuff, we really are talking about, okay, look at our contracts. What are the requirements? Understand what our process engineering and processes are going to look like. What's our process flow, process FMEAs? This is another spot, process FMEAs, where we will be looking for simplifying. Where we like to focus is upstream in the design world, right? We cannot fully realize the benefits if we don't start upstream. Process, yes. Upstream, absolutely. This is where we say you cannot start too early because we have to recognize products, they have functions. That's what the customers want. And those functions have features, and those features have characteristics, and those characteristics requirements or specifications. These are the things that we can see fail, but along that process, these things can fail along the way if we're not paying attention. And the more we look at simplifying, the more we can address those things. So before we go too much further, what's a defect? It's all on the product side. Hasn't met the requirements or the specs. Doesn't meet what the customer needs. And what are some examples of that over on the right? Yeah, parts get reversed, damaged, contamination, mismatched with each other, misalignments, can't be assembled, incoming material, wrong spec, right? Inconsistent dimensions. It's all the stuff that can happen to the part itself, where an error is a deviation more in our process that causes those defects. What happens when a condition is not successful in meeting its process requirements, right? Defects are created by this. We make an error in our processing, right? So it could be omissions, errors on setup, assembly overlooks, wrong piece, operational processes and procedures that aren't right, measurement systems that are not right. These things that are not following their own controls, their own control plans. And so error and mistake proofing, right? There's places where they get designed in different places, right? When we talk about error proofing, it's about prevention, eliminating those factors that cause an error by design. And in the design world, that happens at the design failure modes and effect exercise stage. This is where we're looking. This is where we are changing our designs, right? Control is designed in. Poka-yoke. Now, the next piece, level 2, we call Poka-yoke 100% inspection. Yeah, it's detection and it's about mistakes and errors, 100% inspection. We want to try to stay out of this as much as possible by designing things in. Level 3, Poka-yoke, mistake detection. Yeah, mistake detection. What can we do to make the possibility of a defect caused by an error obvious, so we can deal with it before it gets even worse. So when we look at the overall kind of process, look at this thing, give me a process flow based on some kind of design. Design design failure modes and effect analyses. Feed the PFMEAs. We're going to focus here. We're going to focus here because these other elements, control plans, standardized work instructions, first runs, and ultimately leading to launch, these are our controls that we lock in based on these two exercises. And part of the leading in exercise of this whole thing is a really design for manufacturing and assembly. The links come back. When we talk about DFMEAs, this is what they look like. What can go wrong? What are the causes? How can this be prevented? This is the documentation we will lean on in designing simplicity and controls using DFMA methods, right? Go forward and then go backward. Fundamentally the way it works. DFMEAs, right? How do you prevent? What is it in the current design that we'll put in there? DFMA tools helps drive this part of the discussion. How will the design change in order to make an improvement? So that on the back end, we are trying to avoid having to do a lot of the extra controls and or inspection and so on. Yeah, we do need to make sure we have those controls in there. We should have a quality operating system, but one that's not complex. One that's not complex. And of course, process FMEAs to do the same thing for us. So for a process failure mode, we always, whether it's design or process, we talk about what's the requirement. And then what are the failure modes? How can this thing fail? The first place, an easy place to start is, could it do the opposite of what it's supposed to do, right? Start that way. Supposed to do this, doesn't do it. Supposed to do this, it does the complete opposite. How can this fail? How can this fail? And then looking at the sources of possible failure modes and the controls that we'd have to put on it, the classical Ishikawa, also known as cause and effect diagram, those kinds of, where are the sources of variation that are in this discussion of the failure modes that go into our process FMEAs, it's going back, and our DFMEAs, right? So just to kind of set that up, there's a lot of mistake proofing devices that we can put out there. I'm sure we're well aware. There's lots of different sensors, whether you're stamping, welding, feeding things, there's limit switches, there's all kinds of mistake proofing devices. Now you might be wondering discussion, Mike, when are you going to get to this DFMA discussion? Well, first I want to set up this. There are other engineering tools, design FMEAs, process FMEAs, that we need to focus on with the use of DFMA tools to get the failure modes better controlled and in the limit eliminated. Without that, this is the stuff we're going to be getting into in the manufacturing world. A lot of extra investment and maintenance and possibility for additional error, right? So detection, yes, we need to be able to detect, no question. Can we reduce the amount of detection? Detection controls, yeah, can go from audits to mistake proofing, setups, lab tests. How much of this can we cut out? I'd like you to think about in your own operations. How much of this stuff is out there because the designs are overly complex? Let's focus on some design rules. Think of your designs, and especially in the product development world, when we think about who are our real customers, our first customers in the design world is manufacturing. And if we think of operators, assemblers, machinists out on the floor as our customers, let's think of them as surgeons. So there's minimal setup, minimal activity. They're focused only on the value-added operations, assembling or changing fit, form, feature. You know, we saw the value equation up earlier, but value added is really changing fit, form, feature. So how can we maximize that and minimize operator action, operator activity? Looking at simplifying the parts, general design rules. Let's modularize. Can we take components and neighboring parts and combine them into one? Can we reduce the number of parts? Can we design? We need to think about designing for open spaces so people can have operators, techs can have easy access to get in and do what they need to do. Unrestricted vision. Start to think about your manufacturing systems that are out there, your production systems, your production lines, and all the things that go on there. How busy are your operators? Are they able to see stuff? Or rule number 3, are they doing a lot of reorienting of parts, right? What if we could design better so there's no orientation? It's simple, right? Comes in one orientation, operator picks it up, puts it together. Design parts so they don't tangle. Yeah, how many times have you seen operators untangling things? I worked in a lot of operations where there were a lot of little springs. We used to call them springs and things. And yeah, how can we present parts so the operator does not have to untangle these things, right? Mistake proofing parts that are similar in appearance. Yeah, do you have any parts that they look a lot alike? Maybe you have different customers with similar designs, family of parts, maybe perhaps. And do you ever get them mixed up? Similar parts that aren't actually the same, right? Rule 6, prevent nesting. How about parts that don't sit inside each other and take a lot of effort to pull them apart, right? What can we do in the design side and in the processing side, manufacturing engineering side, so that these things don't lock in each other, right? Conversely to that, self-locking features, those things that should lock into each other, right, are very obvious and easy to do. Rule 7. Rule 8, how about getting rid of all that stuff? Jigs, fixtures, patterns, taps, other equipment, assembly aids. How much secondary and tertiary stuff do we have to have around to put stuff together, right? What can we do in the simplicity of the design, features, forms of the components so we can get rid of some of these things? This all costs money. Oh, and by the way, someone has to design a jig and dies, obviously, and need to be maintained. Fixtures, molds, taps, gauges, someone's got to manage this stuff, right? What can we do to avoid that in the design? Minimizing flexible parts, rule 9, and interconnections. Can we avoid having long runs of stuff that just is like a snake? You know, any kind of molding or molds or any kind of window seals, a great example, any kind of seals that we have to, any kind of, uh, you know, gluing. That's another one that kind of fits in this category. And then rule 10, design in symmetry. Yeah, symmetry can be our friend. And one of the things we talk about symmetry is either make it very it's symmetrical, period, or if there's any possibility to not get it quite right, make it way, way asymmetrical. So here's a couple examples, just kind of very gross examples. Parts that don't tangle. All right, here's an improved design from an open spring with open ends. Parts that don't get interconnected. Is there something we can do to avoid this kind of situation? Just examples. Parts that nest or interconnect. You know, can we do something to avoid some of that? These are all in design and design specification. Here's some things around symmetry. Do I really need it? What do I need? Right? Symmetry. If it looks, do I need to have these ends like this? Does it make a difference? Is it hugely important? Can I design it out? Can I make it either, symmetry is very simple. Do I make it symmetrical? Doesn't matter. And if I can't, then I need to make it as asymmetrical as possible so there's no confusion. My favorite example really, and all this is right here, right? This is slightly asymmetrical. Well, wait a minute. Can I get this screwed up? How long is it going to take to orient this thing properly visually as an operator versus something like this, right? So just thinking about symmetry, it's a huge step. So those are just the general rules. Now there's some additional rules specifically now on assembly. And then we're going to see one more for manual. We'll see a lot of overlap, but number one rule, minimize parts, reduce the number of parts, reduce the number of operations. Well, if I can minimize the number of parts, I should be able to drive number 2, right? Reduction of operations, manufacturing, and assembly. Get these numbers down. Get these numbers down. This is the big cost right here. This is machinery, equipment, tooling, and maybe that goes along with it. Precedence diagrams. Yes, absolutely use those. What is the assembly sequence? Make it very obvious early. Start to work with that sequence as it drives your manufacturing system and design. Allowing for failure recovery. Hey, we all know that there are higher failure items than other in our designs. Well, make them easy to recover from, right? So that they're easy to swap out. This is hugely important also in, I mean, ideally, you want to minimize those in the assembly process. You're going to want to do that there, but especially in serviceability. So think about allowing failure recovery for those high failure items. Product standardization. Yeah, how many times can we reuse something? We should call it where I was investment efficiency, which was about this. Reducing the number of machines that you're buying by reusing components. Reusing, and be careful when you do that, of course. Make sure you develop your parameters and set those in place first before you go into your parts bin and see what parts fit those parameters. But the standardization of parts goes a long way for familiarity in the field, familiarity in the use in the manufacturing system for assembly, and the overall investment cost reduction. Here we are once again making alignment easy. So it's obvious what the alignment might be for the assembly. Making insertion easy. Don't give me press-in tools, special tools that I need for press fits. What can we do to avoid those? Not giving up the requirements we need for meeting the product specifications, but can we make insertion easy? Think of the operator, tech, assembler as a surgeon, right? As a surgeon. Allow for easy stacking, easy orientation, and then fastener design rules. How about having some rules around your fastener selection process, right? Can we reuse fasteners? Number one failure items in vehicles, fasteners, connections, fasteners and connections. Number one, complexity in those same products, fasteners and, and connections. Can we reduce those things? Electrical connections, um, mechanical connections, fasteners and connections. Can we reduce those in the design stage? Driving it even further now to manual assembly. These will sound somewhat familiar. Rule 1, design for accessibility and visibility. Rule 2, insertion easy. 3, can we assemble in one direction, come in from one side, not lift up, over, behind, right? Which then leads to 4, alignment. Make that easy. Symmetrical. Minimize the use of assembly tools, as we've been saying a little bit earlier. Parts easy to handle. Make sure parts that are the same are absolutely the same. Parts that look similar, but keep them away from each other. Differentiate similar parts. This is also where symmetry comes in very important, right? And then back to standardizing parts. Help the operators have a common process for themselves as your products may evolve. Can we keep some level of standardization in our designs? So minimizing part count, just some examples. How many fasteners or whatever you need to fasten things together. Get rid of components as when we're talking about minimizing count part. Um, get rid of components that are just, taking up space. Really? You can add these two with these two, let's call them spacers with what? 4 additional fasteners just because this thing doesn't stack up to it. Can we do something like this? Right? There's a lot of design opportunities in geometries and in size of things. Yeah, this kind of stuff, flexibility, sharp, right? Just kind of gross examples there. Here's self-locating. Yeah, give me a little bit of some kind of alignment to help putting a washer onto a hole. Give me the right length of a pin and it's going into some bore, right? So I can actually have positive feedback that I made it. Um, don't have a whole bunch of different types of fasteners. Reduce the complexity of those fasteners, right? Because that will lead to this. This is a horrible idea. I've seen this in practice where they actually had a little wooden template because of the different types of fasteners, a bunch of M8s and 6s on here. And you can imagine what happened with this. Sounds like a great idea. Oh, we're gonna help ourselves on the shop floor by having a template. Guess what? You bump into things, these go flying all over the place. Give me standard stuff, easy to assemble stuff. You know, give me some conical entry points, right? Give me tapered ends so I can get stuff in there, not squared on stuff which is hard to align. Just a quick example on getting rid of fasteners. Here was the original design. They had 30 parts. They got it down to 10 by being able to look at how can we combine parts that are close to each other, next to each other, not too dissimilar from one another. Got rid of fasteners from 20 to 6, right? Actual assembly time in seconds, 552 to 131 seconds. Costs, these are R&B, cut those down. Costs will come along. Look at complexity. Fasteners are a huge opportunity. Where do you can you look for design opportunities? Look to your DFMEAs, look to your PFMEAs. So how do you evaluate then if you're changing designs? There's 2 major evaluation, primary, highly used methods. First is the Boothroyd-Dewhurst method. Okay, you want to reduce the number of parts. You want to now compare an earlier design to your redesign. Well, Boothroyd-Dewhurst gives us a method to do that. Give me the product information, break it into the individual parts, evaluate the assembly and costs with each of the individual parts, and then have a way to compare the simplicity and compare to other designs. Boothroyd basically does this. Give me the part and we'll reorient it. And he has a method to look at the geometry of the part and how it drives time and the geometry, size, weight of the part and how it drives time in assembly. He has 2 elements that they look at. what we call manual handling and insertion. Handling the part, just getting it into the right orientation, looking at two different angles of rotation around two different axes perpendicular to each other, and the size and the thickness. These are two tables. These got for each one of these handling and for insertion, there's a series of tables. I just provided us a couple examples here. But these tables that Boothroyd developed are based on thousands of different examples of component geometry, sizes, and weights to determine how difficult is it to orient the part in order to assemble it. That's the manual handling piece. And there are timetables for it. And then once the operator has it in the right orientation, how long based on how they're going to attach, assemble the actual assembly process itself, how long that will take based on size, type of process, and so on. So there's a series of tables that Boothroyd uses to break the assembly process into two steps, handling and insertion. And he does it by looking at the geometry of the component, size and weight for both the handling and the insertion, and along with the insertion, the actual process itself for the assembly process. So there's a series of tables, and using an index to compare previous designs to current designs, and a concept that is known as an ideal number of components that an ideal part or subassembly would have, comparing these to each other to see, did I really make an, excuse me, oh, I'm sorry. Did I really make an improvement in the design or not? So as you're going through design iterations to reduce the number of parts, an evaluation method to compare early designs to later designs, Boothroyd gives us a way to do this. The other method is the Lucas method, very similar to Boothroyd, takes the assembly process, breaks it into two parts, looks at feeding and handling, looking at the orientation that you have to get the part into in order to assemble it, and then the assembly process itself. Lucas, this is more a relative complexity, difficulty to do these things versus what, go back to Boothroyd. Boothroyd is actually times, where Lucas is level of difficulty for the different size weights versus, other weights and sizes, and same for the assembly method itself. And I've seen and I've worked with groups where for the Boothroyd Dewhurst, companies will put their own times in these time slots. And with Lucas, they'll put their own relative levels of difficulty for the differences in these orientations and the differences in the assembly methods. And they'll use their own numbers, if you will. Works pretty well. So when we're talking about minimizing the number of parts, 5 good questions to ask. Do they have to move relative to each other? Do you have to be electrothermally insulated? Do they need to be of different material? Will they interfere with other assemblies if they get bigger in size, which they will to a bit? And then service. Will service be adversely affected if we combine neighboring parts? 5 questions to ask. These 5 questions will help us start to combine parts and cut the number of parts out, but we need to ask these questions first. So these are some of the driving questions that you would use with BDI or Lucas. They both start the same way. Give me the component, give me the design, give me the assembly. Break it into individual components. Do the handling and the insertion or assembly evaluations, either BDI or Lucas. You rack and stack for each of the individual components, add those numbers together, and now you can compare design to design. Those are the evaluation methods. Take a look at the manufacturing rules. Same kind of thinking. Give me parts that are simple to make, least intricate shapes, common forms, standard materials, standard design with the product. Can we reuse stuff? Give me tolerances that I can make, match my capability of my machines or my processes. And give me materials that are very processable. Teamwork, hugely important. The voice of the manufacturing people in the design process on the product side and the product input on the manufacturing side. Cross-functional, absolutely. Avoiding secondary operations. Once again, get that other stuff out of there. Expected level of production. Yeah, design your manufacturing system to the level of production you're making. Is it 1 million a year or is it 1 a year? Special process characteristics, what are they? Key in on those. Critical, special characteristics. Those are the ones you want to talk about hitting nominals for and having appropriate tolerancing, right? And then, of course, from the design side, don't tell us how to make it, tell us what to make, and then work together on making that optimal. So, of course, principles around the actual manufacturing side, the process. Everything's driven by the process, matching the volume. Drawings that are manufacturable. Different materials, right? Whether it's mechanical, optical, thermal, color, flammable. We need to consider all those things because it's safety, quality, delivery, cost, always when in the manufacturing world. And of course, environmental impact and statutory regulatory considerations. These are the things we have to think about along the way and controlling costs all the way through. These are what these 5 steps are all about. Getting the costs down, 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 down. I know we've all heard that, through our manufacturing process engineering. So how do you do it? Give me the drawings, tear down the product. Starting to sound like either Lucas or the BDI evaluation methods. Work with your manufacturing and your engineering people. Again, this whole idea of co-location is great, but constant communication among the teams, communication. So how do we get this stuff in there and into our daily routine? Because what I was saying earlier, a lot of the places we've worked with this, everyone says, "Oh, Mike, oh yeah, we evaluate our designs. This one looks always simpler than this." And yeah, but is there a process for it to be drilled in there? Yes. When you're thinking about environment, tooling, customers, and suppliers, and also product development cycle time. Look, if you're going to be designing fewer products, all the way through into development, into the manufacturing system, your product development time is going to be reduced, period. I've had lots of discussions with people. Wow, Mike, it's going to take a while to, do the evaluations and do these comparisons. You cannot compare it if you're making, look, if I can get 20% of your part count down, that's a huge savings, time, quality, cost, and all the other things we talked about, especially when we talk about how that stuff all kind of pushes downstream. I would go so far as to say, all these added, the plan rework, we're supposed to launch up as we map our resources to how APQP is supposed to work. When we get to launch, the whole idea is if you ramp people up, you should get all the problems out at launch. But if you don't, or let me say it this way, if you do have complex parts and products, all this other stuff kicks in. There's all this additional rework, added inspections, and it's 70-85% of the product life cycle is by early decisions up here. Those early decisions should be driven by getting the complexity out of the parts. All right, so I submit it's 90% of it. So work together, product development, product teams to close knowledge gaps. This is a set-based approach that supports what we were saying in APQP. You can always overlay this, but the teams need to work close together with integration points that are also mapped into those phases and gates, right? Converge to reduce the gaps between what is the true capability on the floor, the number of components that we absolutely need to have to fit the form, the function that we need to actually drive and deliver the requirements. It's a narrowing down of open design opportunity, wide open space to what actually works, driving targets, concepts, capabilities, and trade-offs so that there's less rework. There's less rework as you get to launch, which is the point design where you actually can get that waste out. So how do you help with this? To actually get some of these things in. When we put on these classes and the training for these, we talk about steps. First is, let's pick a design rule. All those rules we saw, which I know kind of flew by, this material will be available for you later, but those design rules, pick some that are important to you. How do I pick? Well, look at your current performance on your products that are going through your system right now. Which one are the problem children? Throughput, quality, rework, scrap. How about in the field, serviceability? What are the issues there? Pick the rules that you think you should use to fix some of those problems and build a checklist. Build a checklist. So start with a checklist. pick the rules that you think you want to use. Build a checklist. A checklist that will say, hey, you're going to use these rules, and we want you to think about certain things when you are using these rules. This is the classic checklist. Here's a series of rules that the group decided to use, and the things that they want the designers and the process engineers to consider when they're applying these rules. So tell me what rules to apply, and then what to think about when I'm applying those rules. Build a checklist. And that checklist then can fit into the center part of this overall roadmap. Voice of the customer, give me the original design. You were saying earlier, do a design FMEA, apply some design rules with that checklist, do some design for assembly even further. That's the evaluation. Now the evaluation piece, evaluate the individual components for design for manufacturing. Apply checklists there. Pick a DFM check or rule that you want to use. Apply it. Have a DFM review. Tolerancing at the end. Now, at this point, you're ready to go. Get to prototyping, and you can do your DVP&R afterwards. So some principles around this whole thing. Customer needs. Manage your product development system with these things we're talking about. Cross-functional teams. Integrated process design, which is the same thing as cross-functional teams. Work together. Managing the costs, of course. Don't overlook your supply base. Absolutely involve them. Designs that are robust will result. Of course, any kind of computer-aided analytical tools should be used. Simulate your products. This efficient development for your design and development process, if you integrate design for manufacturing and assembly with a few checkpoints along your gateways, your development process will improve. Absolutely. So be able to continually update that principle 11 as you go forward. Make sure you're aligned with the business strategy. How do you do that? A couple more things and we'll break up here. Come up with a evaluation system. How are we going to measure whether or not we're using DFMA and how well we're using it? Well, some of the things that look at inputs, look at outputs, look at the effectiveness. Determine what you're going to use that information for. Make your evaluation system objective. So I was saying earlier, I don't want to add additional metrics on you. We don't want to do that. But how do you know you're really using these systems effectively, these tools effectively? Come up with some good indicators that cover those points in your product development process where you can evaluate whether or not you're making improvements in your designs through the use of design for manufacturing and assembly. So look at the inputs that you need, look at the outputs, and then act on them. Here's a classic scorecard for design for manufacturing and assembly. Part reduction, non-fastening. Part reuse and carryover. Assembly time reduction, base versus a release. Cost reduction savings come along. Engineering change requirements or requests. Reduction versus previous programs. Change a number of changes versus previous in the current program. Complexity. Fastener complexity. Connector complexity. How much GD&T checking? That's a good one on this program versus previous. And then service standard times. Are they getting reductions from that, from simplified designs? And you can put some scaling on there. This is just a general, maybe measure it red, yellow, green by percentage, how you're delivering on each of these. It's a good way to look at it. So, a lot to consume there. What we're basically saying is there are a series of rules. You saw them. You can apply them. Look at your current issues that you have. Look at your design FMEAs. Look at your process FMEAs. Pick a rule or two that you want to apply to solve specific problems, right? To solve some specific problems. And then go ahead and apply the rules. Go ahead and then apply the evaluation methods, whether it's BDI or Lucas. Omnex can help you with that with training. And when we do come in for training on this, we use your parts, your products, your manufacturing systems, and we put on workshops, a series of them to help you focus in, and then integrate it into your product development process. So quite a bit there, but it essentially comes down to uh, what are some of the issues you think you can address right now? What rules do you think you could apply? Apply them, evaluate them, and then measure that evaluation continually to see that you've got a process and a procedure that starts to become a common practice. It's really where we like to see everybody go. So if there's any other questions, please contact anybody at Omnex. This will be available to y'all. And Andrew, if there's any other closing remarks you'd want to share. We didn't really leave any time for question and answer then. So with that, thank you all for joining. Hopefully this was a fast-paced introduction
Hey, Mike,
to,
we do have
yeah,
one question
okay.
that's come up that maybe you can answer quickly before we step out.
Sure.
Someone asked, DFMA methods have been mostly developed on high volume industries. How could low volume industries such as aerospace or heavy machinery make best use of these methods?
Yeah, great question. We do a bit of work in that. We still focusing on the component level with those, and what we find in the lower volume, there's always an opportunity from complexity, especially at the part level, where how many forms, features, exotic materials do we really need to have, especially like in machine design? Let me go to machine design for just a moment. One of the big issues in machine design, I was a maintenance, guy for quite a long time, and the complexity, maintainability, and reliability have to be measured, typically driven by complexity in the design of a machine. How many different controls, types of controls, um, components, and components that wear that need to be pulled out of a machine for ease of maintenance. We apply design for manufacturing and assembly. We're really looking at reliability and maintainability when it comes to the machine design. In low volume production for products in the field, we still find there's a lot of opportunity in the manufacturing system to reduce those factors that we saw earlier, reduce things like, reduce factors like floor space. Yeah, I've worked with aerospace companies that make two, and those two things get shot off into space. Right. There's always a cost element to that manufacturing side, and it does always typically manifest itself in how much time does it take to actually either make the part, machine the part, um, how much material removal do we actually have to take off of a component to get to what we actually need, right? So we work on those elements of it as well. So in the low volume side, it's really focusing in on absolutely starting, and I don't think I mentioned this in the discussion. We always do start with the assembly. How many parts are in there? With the goal to try to minimize the number of parts. Because the thinking is, if we always start with the assembly, we may focus on the manufacturing piece to help the overall optimization. We always start with assembly though to reduce the number of parts. Why? So we don't have to design a bunch of other parts and manufacture a number of parts. It always starts with, let's reduce the part count. And that still applies in low volume. It absolutely still applies in low volume. And of course in machine design too. Can we design things that just have fewer components that are easy to make and put together? Um, what I like to always share with people are, think of the Kinder eggs, the little chocolate with the assemblable. Can I make my parts snap fit everything? Now, that's like an ideal case, which we talk about in some of those evaluation methods. We do talk about ideal and required versus non-required parts as part of the evaluation. But if you think in simplicity standpoints, can I just make my whole thing snap, click? Probably not. But if we go to that limit, then we start to see some design opportunities. So those kinds of thinkings are what go into the low volume, and especially in aerospace. the lower volume production and machine design, we're always focused on reliability and maintainability, and fewer parts, higher reliability, easy to maintain machinery. And that a jet engine, an automatic transmission, an internal combustion engine, those are all machines, right? And so we like to think about serviceability across that whole spectrum and reliability and maintainability, right? So that would be my thoughts on those.
Thanks, Mike. We have one other quick question. Can this be applied for software development as well?
You know, we did. It's funny you mention it. Yeah, I was working with a electrical, electronic, and embedded software supplier, and we were looking at. It's just the way you categorize defects and errors, and once and you can yeah, yes, you can. It's just defects and errors, and then focusing in on um, the use of DFMEAs for the failure modes of the software code itself. So yeah, and you think about the requirements of the software. I remember I did one of these a number of years ago when we were actually working on some engine control stuff, and the idea was, how does our code fail? And well, the failures are it doesn't meet certain requirements. Start with a DFMEA, right? And start with that. Identify your failure modes, what the causal factors are, and then the corrective actions typically in software are around process. And so that's where then we start to get into the complexity of the code. Uh, and that's where we start to drive, I would say, more elegant code that isn't as voluminous in lines of code. And we have measures actually in our training material. When we talked later today in the last bits of this presentation, we talked about those evaluation methods. We do have complexity measures for software. And so when we get into that discussion around at the code level, we do have metrics there that we use for evaluating whether we're making software actually faster through less code, um, and also looking at the use of upfront, the DFMEA, and then looking at some of these, reducing the complexity of the code, looking at some of these evaluation metrics. So it's a little bit, it's same kind of sequence, but we pick the metric that we are really trying to drive in the software, and then kind of go from there. So yes, we've done it. Actually, I've done it a couple, 3 times in my career, mostly on engine control stuff. And then another one was more of a commercial product, but
Okay, thanks, Mike. I think those are the final questions. So
all
thank you
right,
very much, and that'll conclude today's webinar.
great. Well, thanks for all your time, everyone. Appreciate it. Thanks, Andrew. Appreciate you hosting it. Have a great remainder of your day.